Okay, now we'll talk about the conservation of angular momentum. Look, all the physics are the same. We have the conservation of linear momentum. We have now conservation of angular momentum. It is simple idea, and we can apply many examples and applications using this concepts in physics. If we have a process, rotational process, we or linear process, we have momentum before and momentum after. During this process, for the linear momentum, the momentum should be conserved. For example, the collisions. But if we have also angular momentum, angular motion, or angular process, then the angular momentum before should be equal to angular momentum after. Remember this. The conservation of linear momentum, all of momentums for the systems, the summation of them, which is equal to v initial, okay, is equal to the summation of masses for multiplied by each mass velocity finally. Then the linear momentum is conserved. Also the angular momentum is conserved. So the summation of the angular momentum for each object in the system before or initial is equal to the total angular momentum after. Let us look at this example. We have a rotating disc. A man is moving from R initial, this is R initial, to R final. He comes and walks to this disc is rotating. The man comes from here to here. What is you think or expect will happen? Okay, if the mass of the disc is 50 kilograms, it is constant. If the radius of the disc, R capital, is 3 meters, so it is big disc. If the mass of the man is 60 kilograms, if the man standing at first at 2.5 meters from the center, this is R initially, and R finally, the man comes to a half meter finally, okay? The rotation initially with omega angular velocity is equal to 1 radian per second, okay? What is the final omega? What is the final angular velocity? Is this system will rotate faster or slower from before? We will see that. We need to find omega finally. Okay? We know that now the angular momentum before initial is equal to angular momentum for all the system finally. The angular momentum initially is the angular momentum for the disk, LD, plus the angular momentum for the man initially. We have two objects, the disk and the man. This should be equal to the angular momentum for the disk plus the angular momentum for the man finally. Okay? The angular momentum for the disk is equal not mv as linear momentum. We learned that it is equal to moment of inertia multiplied by the angular velocity. Moment of inertia of the disk multiplied by its initial angular velocity plus the moment of inertia of the man multiplied by the initial omega. This will be equal to the momentum after, which is moment of inertia multiplied by the omega final for each body in this system. Okay, now we don't know I for the disk and for the man initially and finally. For the disk, you can find that from the book, from the given table from the previous chapter. This one. This is the disk rotated around its geometrical center. Okay, it's half mr squared. And the man, we need to suppose it as a point mass, and this is the moment of inertia for the disk, half mr squared, and for the man mr squared, it is proportional to it. We need to suppose that the man is a point mass over that rotated disk. Okay, now the moment of inertia for the disk is equal to half mr squared. Half, the mass is 50 kilograms is given, r is 3 meters, then it will be 225 kilogram meter squared. Kilogram for the mass, r squared has meter squared as unit. The man has two r's, r initial and r final. In this case, the man has two moment of inertias. Okay, the first one, m r squared initially. M1, I give the disk M capital and R capital, and the man M small R small. M1 is 60, R1 is 2.5 squared. It will be 375 kilogram meter squared. And moment of inertia finally, R final is half. Then the moment of inertia for the man finally is 15 kilogram meter squared. That's it. The disk initially and finally, it's the same disk. There is no change on this the shape of that disk. Okay, we have now we have find I, and we have omega initial. We need to find omega final. It's done. Now, moment of inertia for the disk. Again, this is the formula. Initially and finally. Okay, moment of inertia for the disk is 200, as we find there. 25 multiplied by omega, which is 1 initially. Moment of inertia for the man 375 multiplied by omega, which is 1. This will be equal to I take omega final out from the two terms. It is easy to be understood. Moment of inertia for the disk, it's the same as initially, 225, and the moment of inertia for the man is 15 finally. Moment of inertia of the man, look at that. Initially it was 375, then it will be 15. It decreases in high ratio because his radius of rotation is very small with compared with this one, which is, this one is half meter, this one is 5/2 meters, it is 1/5. Okay, now I just put the numerical values. This will be equal to 600 is equal to 140 omega final. Just divide both sides over 240, then omega final will be equal to 2.5 radians per second. Look, omega initial in this example is 1. Omega final is 2.5. It increases, okay? When our system is collapsed to the center of rotation in the final situation here, its speed is raised. Okay, you can solve many examples like this, and you can remember when the dancer open his hand or her hands, her velocity is low. Then when it collect her hands to her the nearest point to axis of rotation, then the omega rotation will be raised. In this case, the angular motion is less than in this case. We know that, and we will see many videos inshallah in the Canvas. Okay, please solve many examples about this. You can also look at this example. This example is simple also because it is a rotational collision. Just you need to apply L initial is equal to L final. Okay, all the examples are the same. Just you need to apply this formula. Thank you.